Andy, now we discuss some important points, some areas where we have to focus from polymers. So from polymers, mainly you may concentrate on three concepts, and one is Mn bar, number average molar mass, weight average molar mass, and polydispersity index. Okay, mainly you may focus TSGENCO aspirants on these three, and number average molar mass, weight average molar mass, and polydispersity index. And some other points I will explain from polymers, but mainly you may focus on these three. And okay, so first of all, what are polymers? And polymers are nothing but what? They are high molecular weight compounds. Their molecular weight is very high. They contains large number of repeating units. Repeating units are nothing but monomers. Large number of monomers they contain. Those monomers are connected each other by what? Covalent bonds. Those monomers arranged over and over again to form large molecule, big molecule, that is called polymer or macromolecule. Okay, they are connected by what? Monomers are connected by covalent bonds. And some examples for macromolecules or polymers, if you see naturally occurring polymers, we have, for example, biopolymers, proteins, nucleic acids, DNA, all these are what? Biopolymers. Next, some other naturally occurring polymers, if you see, cellulose, silk, wool, natural rubber, okay, all these comes under what? Natural occurring polymers. Next, synthetic polymers are man-made polymers or artificial polymers. If you see polythene, polystyrene, nylon, Teflon, etc., all those are examples for what? Artificial polymers. Next one, degree of polymerization. And what is the degree of polymerization? Degree of polymerization indicates what? How many monomers are present in a given polymer? How many monomers present in a given polymer? That is called degree of polymerization. I am indicating as P here. How many monomers are present in a given polymer? Okay. Okay, how to give that? And that we can give by like this. And that is the mass of polymer by molar mass of monomer. Small m indicates mass of polymer, capital M indicates molar mass of monomer. For example, if molar mass of monomer is 10 units, molar mass of monomer is 10 units, and mass of polymer is 200 units, then what we will get in a degree of polymerization? 200 by 10. That means that polymer contains how many monomeric units? And 20 monomeric units. Each monomeric unit mass is 10. So 20 into 10, we got polymer mass 200 units only. So degree of polymerization we can calculate like this: small m by capital M, where small m is the mass of polymer and capital M is the mass of monomer. Okay. During polymerization process, while we are preparing polymers, the problem is the reaction may be stopped at any stage, and the reaction may be stopped at any stage. The chain termination may occur at any stage. So because of that, we may not get all polymers with the same molar mass. All polymer molecules may possess a different number of monomers. All polymer molecules may not have same number of monomers. That means they may not have same molar mass. That is the problem we have. That's why we cannot calculate absolute values of molar masses for polymers. So we can give what? Average molar masses. So we can give average molar masses. Why we are giving average molar masses? If you prepare a polymer sample, whether all polymer molecules possess same number of monomers or different number of monomers. All polymer molecules may not have same number of monomers. That means all polymers may not have same molar mass. That's why we give average molar mass. There are 4 ways by which we can give average molar mass. The first one is number average molar mass. Second one, weight average molar mass. Next, viscosity average molar mass, and Z average molar mass. In that you concentrate on first two, number average and weight average molar mass. And you just remember the formula, and this is nothing but arithmetic mean of molar masses. And total mass of polymer sample by total number of molecules. Total mass of polymer sample by total number of molecules, that gives number average molar mass only. That means summation I Ni Mi by summation I Ni, and this is the formula for number average molar mass only. Okay, N1 polymers have molar mass M1 and N2 polymers have molar mass M2, and Ni polymers have molar mass Mi. Okay, then what about total molar mass we will get? Sorry, total mass of polymer. N1 into M1 indicate mass of first type of molecules and polymer molecules. N2 M2 gives total mass of second type of polymer molecules. Ni Mi indicates mass of ith type of polymer molecules only. Okay, now the sum of all these gives what? Total number of polymers only. Total number of polymer molecules, that is nothing but summation I Ni. So this summation I Ni indicates what? Total number of polymer molecules only. This numerator indicates what? Total mass of polymer. So the ratio of total mass of polymer to total number of molecules, that is called number average molar mass. Otherwise we can also give like this, and that is the sum of the fraction of molecules multiplied by their corresponding molar mass only. Fraction of molecules means we'll get some Ni by N and Ni by N. So that if you substitute, same we'll get summation I Ni means N only. Summation I Ni is nothing but what? N only. Okay. So this is the number average molar mass. How to determine number average molar mass experimentally? That we can determine by using osmometry. And number average molecular mass we can get experimentally by using osmometry, that is based on osmometer, instrument name osmometer. The principle involved is osmosis, and based on osmosis or osmotic pressure we can calculate and number average molar mass. Now the second one is weight average molar mass. Weight average molar mass, the expression is, that is nothing but summation I weight fraction multiplied by the corresponding molar masses. And here fraction of molecules we are multiplying with corresponding molar mass. Here weight fraction of each type of polymers, and weight fraction of each type of polymers we have to multiply by corresponding molar masses. The formula we get like this, and just remember this formula. Summation I, in the numerator you add 1 Mi, in the denominator also you add 1 Mi, and so we'll get Ni Mi square by summation I Ni Mi, and this is the expression for weight average molar mass. Okay, and this weight average molar mass experimentally we determine by using light scattering method. And just you determine what is the method we follow to determine MW bar, that is light scattering method. To determine N bar, osmometry method we follow. Okay, now what is the product of Mn bar and MW bar? Previously this question given, and what is the product of these two? And Mn bar means what we have summation I Ni Mi by Ni, and so summation I Ni Mi gets cancelled, so we'll get summation I Ni Mi square by summation I Ni. Otherwise this summation I Ni we can write as N, that indicates total number of particles only. So N inverse summation I Ni Mi square. This is the product of the first two average molar masses only. Next one, another concept and polydispersity index. And polydispersity index, what is the importance of polydispersity index? Polydispersity index explains heterogeneity of polymer sample. How weights of, how molar masses of polymers are distributing. What is the width of molar masses? That is given by polydispersity index. And for example, polymer sample, for a given polymer sample, the weights are distributing like this, and 100 to 5000. Another polymer sample we are taking, the weights are distributing like this, and 100 to 10,000 and okay, where the distribution is high and where the heterogeneity is high, and in the second case heterogeneity is high. Okay, molecular weight distribution is high, so therefore polydispersity index for second compound, second polymer sample is more compared to first sample and okay. So width of distribution of molecular weights, that is given by polydispersity index, or heterogeneity of polymer sample, or how molecular weights are distributing, that is given by polydispersity index and now how to calculate polydispersity index, and we can calculate polydispersity index like this. That is nothing but the ratio of weight average molar mass to number average molar mass. That is the ratio of weight average molar mass to number average molar mass. If you take a monodisperse polymer, and if you take a monodisperse polymer, if you take a monodisperse polymer, that means all polymers have same molar mass, and if all polymers have same molar mass, then number average molar mass and weight average molar mass becomes same, and mw bar becomes equal to mn bar. If you want, you may substitute in the place of m1, m2, m3 and so on as m only. All molar mass, all polymers have same molar masses, and in the place of m1, m2, m3 you may substitute m, you will get same, and mn bar and mw bar both we will get same. That means if you take a monodisperse polymer, what is polydispersity index value? 1, and if you take a polydisperse polymer, if you take a polydisperse polymer, that means all polymers may not have same molar mass. All polymers may not have same molar mass or same number of monomers. In such case, mw bar is not equal to mn bar. So polydispersity index value is not equal to 1. But it is observed that for polydispersed polymers, we will get mw bar greater than mn bar. And we get mw bar is greater than mn bar. That means we will get polydispersity index value greater than 1. Okay, this is the concept of mn bar, mw bar and polydispersity index. And okay, so we may expect problems also. They may give polymer sample with number of polymers and n1 and n2 for example, their corresponding molar masses, and we have to calculate mn bar and mw bars. Simple substitution only. In the given equation we have to substitute, and mostly they may give two types of polymers, and two types of polymers, then we will get what? m1 n1 plus m2 n2 by n1 plus m2. Here n1 m1 square plus n2 m2 square by n1 m1 plus n2 m2, and like this we can calculate it. So mainly you concentrate on these three concepts from polymers, and other than this you may study what different types of polymers. You follow Puri Sharma, it is clearly given different types of polymers. You may study that. Okay, and some other concepts I am giving here. Next, some more concepts you may focus if you have time. The first one is Mark-Kuhn equation, and Mark-Kuhn equation. Mark-Kuhn equation. This gives the relation between viscosity. Before that, third average molar mass, that is mz bar. Third average molar mass, that is mz bar. Okay, the formula for mz bar is summation I. Now you add one more mi and in the numerator and denominator, and this is the formula. So previously we got NiMi square for the mw bar by NiMi. Now you add one more mi in the numerator and denominator, that is mz bar, and z average molar mass, that is called as z average molar mass. In German, z means centrifuge and centrifuge. Okay, this is calculated by ultracentrifugation, and this is calculated by ultracentrifugation. So that's why it is called z average molar mass, ultracentrifugation or sedimentation method. Experimentally, this mz bar is calculated by ultracentrifugation or sedimentation. This is about mz bar, and fourth one is viscosity average molar mass, and viscosity average molar mass, viscosity average molar mass, mv bar. This is similar to mw bar, and this is similar to mw bar. We have summation I ni mi by summation I ni mi. Here we will get whole power here 1 by a, whole power we will get 1 by a, mi power 1 plus a we will get. The possible values for a are 0.5 to 1, and the possible values for a are 0.5 to 1. This is called viscosity average molar mass, and viscosity average molar mass. Okay, if a is equal to 1, what we get? If a is equal to 1, we get mv bar is equal to what? Summation I ni mi square by summation I ni mi. This is nothing but what? Mw bar. That is nothing but Mw bar. So if a value is 1, a is a constant, its values changes from 0.5 to 1. If a value is 1, then both viscosity average molar mass and weight average molar mass both are same. And so these are the 4 ways by which we can give the average molar mass of a polymer sample. What is the relation between these 4 average molar masses? If you see, Mn bar is less than Mn bar is less than Mv bar is less than Mw bar is less than Mz bar, and this is the relation between these 4 average molar masses. And okay, if A is equal to 1, then what we have? Mn bar is less than Mv bar is equal to Mw bar is less than Mz bar. Simply you remember in the alphabetical order, and in alphabets first we will get N, after that V, after that W, after that Z. So you just remember in the alphabetical order, and okay, and if A value is 1, both are same. Weight average molar mass and viscosity average molar mass both are same. So in that, number average molar mass is determined by what? Osmometry. Okay, viscosity average molar mass is determined by viscometry. Viscometry, based on viscosity values we can determine it. Weight average molar mass, light scattering. Z average molar mass, what? Sedimentation or centrifugation. Sedimentation or centrifugation method we follow to determine these molar masses experimentally. Okay, these are the 4 ways of expressing average molar masses of polymers. Okay, so next I am giving Mark-Kuhn-Howing equation. Mark-Kuhn-Howing equation. So this equation gives how to determine viscosity and viscosity average molar mass. So for that we have to calculate intrinsic viscosity, and this is the formula we have, just you remember, mv bar power A. This is the formula we have. By using this equation we can calculate viscosity average molar mass based on intrinsic viscosity, and this is called intrinsic viscosity. K and A are called Mark-Kuhn parameters. They are called as Mark-Kuhn parameters. They depends on nature of solvent we are taking, polymer we are taking, okay, and temperature. And K comma A values depends on solvent, polymer and temperature. By using this equation, what we can calculate? Viscosity average molar mass we can calculate. And for example, we are taking 2 polymer samples. For first polymer sample, parameters we have like this: K1, A1 and viscosity average molar mass M1 bar. And for second polymer sample, the parameters we have K2, A2 and viscosity average molar mass we have M2 bar. Then from Mark-Kuhn equation we will get K1 M1 bar power A1, that is equal to K2 M2 bar power A2. So based on this equation, if Mark-Kuhn parameters are known to us, one polymer sample molar mass is known to us, another polymer sample viscosity average molar mass we can calculate. Okay, so Mark-Kuhn-Howing equation gives relation between what? Intrinsic viscosity and viscosity average molar mass. Okay, this is Mark-Kuhn-Howing equation. Next, another one, kinetic chain length. Kinetic chain length. For example, if polymerization process is following free radical mechanism and polymerization process is following free radical mechanism. For example, in the first step some free radical is produced. This is called chain initiation step. In the next step monomers are attached like this and MR. Next like this monomers are attached and M2R. Finally MNR plus MNR. Chain termination, these are what chain propagation steps. M3R, M4R, like that we will get. Finally we may get MN R, MN R, like this and okay. The first step is what? Chain initiation, chain propagation steps, chain termination steps and in the first step some chain initiator free radical is produced. After that monomers are attached, chain propagation steps, and finally chain termination step. Okay, if polymerization process follows free radical mechanism, then kinetic chain length indicates what? On an average how many monomers are present in a given polymer. On an average how many monomers are present in a given polymer, that can be calculated as kinetic chain length is given as rate of monomer depletion. It is the ratio of rate of monomer depletion to rate of propagating radical formation. Rate of propagating radical formation. This ratio gives kinetic chain length and rate of monomer depletion, where monomer is consumed and monomer is consumed in the propagation steps. So that is nothing but rate of propagation steps. Okay, rate of propagation radical formation and where chain initiator is produced and in the first step. So rate of initiation step and rate of initiation step or rate of activation step and rate of propagating step is nothing but rate of overall reaction and rate of overall reaction by rate of initiation step and rate of overall reaction we can give like this and minus dm by dt by chain initiation step and for example chain initiation step rate constant k1, rate is equal to what? Rate constant into concentration of reactant. Okay, so rate of monomer depletion we can give as minus dm by dt, rate of monomer consumption and where monomer is consuming in the propagating steps monomer is consuming, that's why that is nothing but rate of propagating steps by rate of initiation steps, where propagating radical is forming and in the first step propagating radical is forming, that's why rate of initiation step or rate of activation step. In the propagation steps decides overall rate of reaction, that's why rate of overall reaction by rate of initiation step. Rate of monomer consumption is given by minus dm by dt, rate of initiation step first step k1 into concentration of I. So they may give you this rate of consumption of monomer and k1 value, concentration of I. Okay, they may give you those three parameters. They may ask you to calculate kinetic chain length. Kinetic chain length indicates what? On an average in each polymer how many monomers are present. Okay. This is about kinetic chain length. Next in your syllabus kinetics of polymerization mentioned. Mostly we may not expect questions such depth. I am explaining briefly that kinetics of polymerization also. Okay, if you take condensation polymerization some small molecules are removed. Generally water molecule is removed during condensation polymerization and we will get a polymer molecule. Okay, let us consider initial concentration of A is M0, initial concentration of B monomers M0. After some time T and at 0th time, after some time T, the concentration of A is M, remaining concentration is capital M and concentration of monomers after time T. For example, if it follows second order kinetics and if it follows second order kinetics. That means rate is proportional to a power 1 b power 1 and rate is proportional to a power 1 and b power 1. Then it follows second order kinetics. We know according to second order kinetics what we have and 1 by a minus 6 is equal to k2t plus 1 by a we have. Similar concept if you apply here, 1 by remaining concentration of polymer at time t, that is 1 by m, that is equal to k2t initial concentration of monomer, that is m naught. Initial concentration of monomer is m naught. So if you multiply this equation with m naught, we will get m naught by m, that is equal to k2, we are multiplying with m naught plus t plus 1 we will get it. Okay, just we are taking condensation polymerization, two molecules undergo addition. During that a small molecule may be removed, generally water molecule may be removed. Okay, so if it follows second order kinetics, and this is the expression we have for second order kinetics. Remaining concentration of monomer m, okay, initial concentration of monomer m naught, that we substituted and we multiplied with m naught. But m naught by m is nothing but xn bar. And what is xn bar? Xn bar is called as number average degree of polymerization and number average degree of polymerization. So that indicates what? Degree of polymerization, and that indicates degree of polymerization. Okay, so here we can write xn bar is equal to k2 m naught t plus 1. So therefore how degree of polymerization changes with the time, that we can give based on this equation. So degree of polymerization changes linearly with the time. This is in the form of y is equal to mx plus c. So how degree of polymerization changes with time? Degree of polymerization changes linearly with the time. Or this equation we can write like this also. We have one equation and Carruthers equation. Carruthers equation. According to Carruthers equation, degree of polymerization is given as 1 by 1 minus p, and 1 by 1 minus p, where p indicates fraction of monomers converted to polymers, and fraction of monomers converted to polymers. That is nothing but what? Initial number of monomers we are taking as m naught, and initial number of monomers is m naught. Okay, in that how many are converted to polymers, and that means initial concentration minus remaining concentration. Initial concentration minus remaining concentration. Okay, that gives fraction of monomers converted to polymers. And so this is the expression for P and 1 minus m by m naught, and 1 minus m by m naught and P. Okay, m naught by m means what? Xn bar, and xn bar, that if you substitute finally you will get this equation. And okay, Nandi. So P is nothing but fraction of monomers converted to polymers. And so what is the relation between fraction of monomers converted to polymers, extent of reaction, and what number average degree of polymerization? That relation is given by what? Carruthers equation. So therefore here we can write Carruthers equation also. 1 by 1 minus p is equal to k2 into m naught into t plus 1. Okay, so how fraction of monomers converted to polymers, that is changing with the time, that also we can study based on this equation. And this is the kinetics of polymerization mentioned to you. And okay, similarly we can apply for third order also, and not required, that much depth may not required. And similarly we can apply to third order also. And okay, and from this Carruthers equation here we have xn bar is equal to 1 by 1 minus p. And for example, 98% of monomers converted to polymers, and fraction of monomers converted to polymers is how much? 98%, is 0.98. And then what is the degree of polymerization? And 1 by 1 minus 0.98, that means 1 by 0.02 we will get, that means what we get, and 100 by 2, that is 50. And for example 99% converted, and what is degree of polymerization? And 1 by 1 minus 0.99, that means 1 by 0.01 will get, that is 100. And like this we can calculate degree of polymerization based on fraction of monomers converted to polymers. So that relation is called as Carothers equation. And right, these are some points you may remember from polymers. And in addition to this, you may refer from Puri and Sharma what are the different types of polymers. Mostly you concentrate on those three, and Mn bar, Mw bar, and polydispersity index. And thank you.